Lecture 4. And this one has something that's probably a lot of your favorite from Chem, significant digits. We're going over them here, and we're going over them again in the big review because we do try our best to use them with AP Chem. Had a professor tell me they're nice, try your best, but in real chemistry, not on the AP test, not on one of those things where I want to see if you can do it, keeping close to the right number is good. We're going to try to look a little bit more at why significant digits are a thing, and then use them throughout the year. The first idea that makes them why they're a thing or not is exact versus inexact numbers. Some numbers are called exact numbers because you know them exactly. If I were to be like, all right, well, count my pens. I got a couple here. Looks like I have 3. I can tell you exactly 3. I can tell you 1, 2, 3. That was easy. There was no question. There's not like a 4th sticking to my hand. I didn't pull one out from behind my ear. There were 3 pens. We good. Exact numbers are known exactly. They are not measured. They are counted. How many of you are in this class? Exact number. If I look down at my feet, because I am barefoot, because it's May, and so I'm barefoot, I see 10 toes. Exactly 10, and I can count them. I see 10 fingers, exactly 10. 1 watch, 2 ears, we good. Exact numbers can be counted exactly. Inexact numbers are not known that exactly. They're determined by measurement. If I want to know how much I weigh, I get on a scale and I look down and it tells me. But that's not exact. That's measured. Measured is inexact. So if I wanted to look at how tall I am, same thing, I would measure it. There you go. Inexact numbers. Those are the ones we do the significant digits and we round and all of that good stuff. So for exact or inexact here, if I'm measuring the length of the cat's tail, if you've ever tried to do that, it's not easy. They're not a fan. It's their tail. It's not your tail. I'd have to measure an inexact number. Mass of a 20-ounce bottle of Mountain Dew? Mass. I need to measure it. Even though you got some volumes on the side, those again are measured. So they're inexact. Number of freshmen in the school. I can count them. I can go 1, 2, 3. So that would be exact. And the volume of air in this room, or your room, or any room, would be inexact because it would be measured. So there's your big idea on that one. Turning my page, accuracy and precision with the little targets. I think every chem class that I've ever taken did accuracy and precision with the targets. Accurate and precise, even though they're used interchangeably in everyday talk-ins, are different in science. Accuracy, how closely individual measurements agree with the correct or true value. So it's looking at how close a measurement is to the desired value or the actual value. So if I'm trying to throw something away into a garbage can, I had some classes that love to do this. Throw it into the garbage can. If I hit the can, it's accurate. If I hit the can multiple times, I got a pretty accurate shot going. Precise talks about how close values are to each other, not how close they are to what I want. So let's say that you're taking quizzes once a week. Accurate would be 10 out of 10. And you're scoring 3 out of 10 every week. 3 out of 10. Man, are you consistent? Man, are you precise? But a 3 out of 10 versus a 10 out of 10, I'll take the 10 out of 10. I'll even take an inaccurate value where I get 8, 9, or 10 out of 10 rather than being precise at 3 out of 10. The examples of accuracy and precision I gave you in your packet are the classic, the bullseye. Both accurate and precise clustered in the middle. Precise but not accurate, clustered outside the center. Accurate but not really precise is spread out around the bullseye. And the way I would have them, they're just sort of all over. They may not even hit the target if I did it. Not accurate or precise. Neither accurate nor precise. There's my grammatically correct version there. Significant digits. All digits of a measured quantity, so we're talking in exact numbers, all digits of a measured quantity, including the uncertain one. So the way we do significant digits for measurement, you measure, you get all the numbers you can out of what you see, and then you estimate one. If I get on a scale, I'm good. I got on my scale, and it says 136.0 pounds. Okay, well, I could guess another one. If I stand on it and it ain't moving, I'm saying 136.00. I'm going to estimate that last digit because it's not moving. So let's try this a different way. If I get on a scale and it goes 135, 136, it's one that only has to the nearest digit no 0.0, mine's 0.0, and it goes 135 and 136. I know I'm somewhere between the two. If I do that and it goes to 136, I'm going to guess that and you say you have to guess one. So I know I'm somewhere between 135 and 136. I'm going to go 135.6. I'm going to estimate that I'm just over halfway to 136, and that's why I did that weird wobble, and that it rounded up. If I did the weird wobble, and it went down to 135, I would guess I was 135.4, just shy of midway. And again, that's why I got the wobble. So I'm going to estimate 1. Go to the pictures in your packet. I'm not trying to draw graduated cylinders on this thing. If I look at the beaker on the left, and it says read each of the following to the correct number of significant digits. The numbers I can see on that beaker are 20, 40, 60, and 80. I see little lines in between that would be 30, 50, and 70. It looks like my water level is somewhere between 40 and 50, but much closer to 40 than 50. 40 would be my estimate with one significant digit, only the 4. I can guess one more. 42 milliliters, 43 milliliters, the 40 I see, and one more digit. My graduated cylinder, ooh, look, more lines than a beaker. I have a line every milliliter in that graduated cylinder. I see 35, and if I count, I have 36, 37, 38, and 39, between 35 and 40. So I am 35, 36. I definitely know it's 36 point something. It's halfway between 36 and 37. Real quick, look, the little number at the bottom, big number at the top. We work our way up on beakers and graduated cylinders. So I'm thinking like 36.5? I'm halfway between. Good. What am I measuring there? It looks like I'm measuring a nothing. But it's on a ruler, and it's a ruler in, I can't even see if that, I guess it's in inches. I couldn't even see what it said. Inches, sure. If I look, it looks like I'm around 1.1 for sure, and it's sort of between. Because I can see 1.1 for sure, I can guess another digit and go to 1.15. I can read and then guess one. Counting significant digits. 4 rules. Everybody's favorite, and then we'll do the practice. All non-zero, that's your first blank, all non-zero digits are significant. So 1 through 9 are always significant. We don't write them unless we need them. Zeros between, second blank's between, non-zero digits are significant. So if I say my room number 206, the 0 is significant because it's between the 2 and the 6. Zeros at the beginning of a number are never significant. So like 0.005, the zeros aren't. They're at the beginning. Zeros at the beginning are never significant. Zeros at the end of a number are significant if the number contains a decimal point. We can even tack a fake one at the end to make them matter. So your blanks are non-zero between, at the beginning, and at the end. And there you go. Let's do these. And then we'll look at the rules for calculating too. We should have time. 1005. 1 is, 5 is, so the zeros are too for 4 significant digits. 5.600. Got a decimal point? So they're all significant. 4. These zeros are at the beginning. So I go across till I get something that isn't a 0. 2 significant digits. If you have an exponent, the exponent stuff doesn't matter. 3 significant digits. In 4,000 point, that decimal point makes them significant. 5 and 2 and everything in between. Sandwich rule, field goal rule, whatever you want to call it, all the stuff in between matters for 6. This one's tricky because the number at the beginning, this is 2 different rules. Because I said if you have a decimal, zeros count, but numbers at the beginning don't. Rule 3 comes before Rule 4. So the 0 at the beginning does not, but then the decimal point makes the 1 at the end significant. That's sort of I don't like rules like that. I don't like rules where one has to beat the other. I think I said already I don't like organic chem, and that's how it works. So there we go. Scratch out my exponent for 2 significant digits because of the decimal. There's no decimal point in 200. 1 significant digit. We're coming back to these in the practice after I do all these lectures. We got the 10 important things to know. Significant digits in calculation rules. The goal of this whole plan is to report the final answer with only 1 uncertain digit. It's really tough to see that as you work through them, but the rules do plan for that. If I add or subtract numbers with where I've counted significant digits, if I add or subtract, I keep the lowest number of decimal places just after the point. It's where I'm looking. My lowest number of decimal places. In my example, I add 65.005 plus 17.1. 17.1 has only 1 digit after the decimal. That's the one I'm keeping, so I round to 82.1. When I multiply, do multiplication and division, lowest total number of significant digits. So it's different. If I multiply or divide, I'm looking at total number of significant digits. If I add or subtract, I look after the decimal only. So, if you're working through a problem with a calculator, don't round until the end. So, there you go. Keep that in mind. Don't round till the end. Keep all of those significant digits as you run through these, and then round when you're all done to get a better answer. We'll talk more about that as we go. Lecture 4 done.